Alright, welcome. In this video, I'm going to be working the Algebra 2 Unit 2 test review. So we're going to be practicing our systems of linear equations, our substitution, our elimination with 2x2s, with 3x3s, with systems of inequalities, all that good stuff. So we're going to start off with just solving a couple of systems, just the old way, right? Solving algebraically. And, you know, one like this especially, but really any of them, I just want to re-emphasize, I'm encouraging you to look at the system, try to determine which technique is going to work best for you, substitution or elimination, and then do that, right? No matter what. What it suggests you might do, the best thing for you to do is going to be just do whatever you think to do first. Your first instinct is going to be your best instinct. So I'm going to just substitute on y here because I see I can solve for that y. Okay? You could definitely do elimination on this, but then, you know, it's going to get you the same thing. And if you want to do elimination on this, that's what you should do. Okay, so I'm going to solve for y in the first equation, and I'll have y equals 27x minus 43 by subtracting 43 from both sides. And then I'm going to substitute on this y. So 18x minus 27x minus 43. That's going to equal negative 15. Okay. Then I'm going to subtract 18x minus 27x plus 43 equals negative 15. And then I'm going to subtract this, and I'll have negative 9x's plus 43 equals negative 15. Okay. So I'm going to need to subtract 43 from both sides. And I'll have negative 9x equals negative 15 minus 43 more is going to be negative 58. Now, 5 plus 8 is 13, and 9 does not divide 13, so I know that 9 is not going to divide negative 58, right? Because if a number is divisible by 9, the sum of its digits is divisible by 9 as well. And so I know that I'm just going to say x is going to have to be 58 over 9. And I mean, that's not the best number I've ever seen, but it's not the worst either. And remember, not all the answers are always going to be integers, so can't always just assume that. Doesn't necessarily mean you've gotten down the wrong road if you've gotten this answer. Okay, now I've got a formula for y. That's 27x, but I'm going to just call that 27 over 1 because I know I'm multiplying by 58 over 9. And I'm not really interested in doing 28 times 57, so I'm going to try to reduce that a little bit. But then I'm going to subtract 43 afterwards. Okay, so I can say 27 over 9, that's the same as 3 over 1. And 3 times 58, well, I've got a better chance of multiplying that accurately. Okay, 3 times 58, well, 3 times 50 is 150. 3 times 8 is 24. So I've got 150 and 24 more is 174 minus 43 equals 131. Which I did check this one, and, well, it seems like, yeah, I got a y coordinate of 131, so this is the right answer. If you're ever unsure, you can go back to the original two equations and check on both of them, and if these coordinates satisfy both equations, then it's the solution to the system. Okay. Oh, a rough one to get you started on, but you know, good reminder, not always going to come back integers. Then we've got one here that's set up real nice for elimination. So I'm going to do elimination on y because I've got this negative y here and the 4y there. I'm going to multiply this whole top row by 4. So I'm going to have 8x negative 4y equaling positive 4. And then I'll have 8x plus 4y equals 6. Okay. We're going to add these together to get 0 y's. Don't lose sight of what we're doing here. We're going to add 8x plus 8x, and that's 16x's equals 10. Okay, so I'm going to divide both sides by 16, and I'm going to get 5 divided by 8. Okay. And then 2x minus y equals 1, so 2x with 10 over 8 minus y equals 1, which I'm going to call 8 over 8. Right, because then that makes it much easier to solve, right? You can see 10 over 8 minus some number is equal to 8 over 8. Well, that's going to have to be 2 over 8. So y equals 2 over 8. And then that's going to be my solution, right? You could call that 1/4. If it was a multiple choice, you would easily be able to recognize that 2/8 and 1/4 are the same number. Yeah, there you go. All right, now we're going to solve these by graphing, which is not a technique that I use a whole lot in my class, but it's a technique that works. And it's good that we understand what we're doing when we solve by graphing, okay? So this is going to be y equals -4x plus 8. And that's going to be troublesome because this grid only goes up to 7. Okay, so I'm just going to say, all right, what's going to be the value of y when x is equal to 1? Okay, I'm going to plot 2 points and connect the dots, and because I know the slope's going to be -4 when I subtract 4x. So when x is 1, I've got 4 plus y equals 8, so it's going to be 1 and 4. And that makes sense, because if I was up here at 0 and 8, and I went over 1 down 4, well, that's what I'm going to get another point here. Okay, that's going to be enough for me to sketch this line. And yeah, I think this is going to be good. But solving by graphing is really high stakes because your graphs have to be super accurate. Otherwise, you're going to be like, does that really run into each other at the grid intersection point? And then you'd be like trying to check on the equations, and that's basically substitution. So that's why I generally tend to recommend we use substitution elimination to solve these systems. Okay, 2x minus 3y equals 18. Maybe I will say, oh, okay, the x-intercept on this one's going to be 9, and that's, again, going to be off my area. So the y-intercept would be -3y equals 18, so y equals -6. That's on. And then I just need to find some other point that would work. What's the slope of this thing going to be? It's going to be 2/3, so it's going to go over here. I'm cheating a little bit by thinking about what's going to happen when I solve for y. I'm going to have -2x divided by -3, and I get positive 2/3. All right, so yeah, we've got these, and okay, you can see that that spot right there, that's supposed to be where they're intersecting, and that's going to be our solution. So I'm going to say x equals 1, 2, 3, and y equals 1, 2, 3, -4. So my solution is 3 and -4. But that depends on us having a very accurate graph. If you don't have a straight edge, my recommendation is that you plot each point on the grid and connect the dots. Because presumably, if you're asked to solve by graphing, then the solution will be at a grid intersection point. That would not be the thing to do to ask you to solve by graphing where it was like 4.5 or something. That would be too hard for you to see. Okay. 2x plus y equals 6. So y equals -2x plus 6, 2, 4, 6. Maybe I'll do that way. Say you don't have a straight edge and you're not sure what I was talking about right there. Plot every point. Well, I'm going to go over here and I'm going to go over 1 down 2 because this is y equals -2x plus 6. Okay, and then I'm going to go over 1 down 2, and I'm just going to keep plotting these points because presumably the answer is going to be a... Is this going to be, I don't actually know what's going to happen. It's going to be a grid intersection spot. So, I'm just going to go like that. And hopefully it'll be one of these points right here. All right, and then this is not solved for very well. Okay, I'm going to, I guess, subtract 9 from both sides. And then divide by -3. Okay, yeah. So y equals -2x plus 3. Okay, this is going to have just slope of -2. It's just going to have the same slope. And it's a parallel line, and we see that they are not intersecting. Okay, so this one would have no solution. So really, I think, more so than the skill of actually graphing these and seeing where they run into each other, it's the understanding that when we're solving a system of equations, we're plotting some equations and we're seeing where they all run into each other, where they're simultaneously true is going to be the intersection points. That's going to be a concept we're going to come back to later on in the course, especially once we start using technology to solve equations. And then that's something you'll want to do in your next courses as well in pre-cal and calculus. Okay. So y minus 3 is less than -1/4 x. I'm going to add 3 to both sides, just like on the piece of paper. Okay, so -1/4 x plus 3. negative 1/4. So it's going to go up 1 when it goes over by 4. And this is going to be a dotted line scenario. Okay, that was not very good, but not using a straight edge this time. So 2x minus 2. So negative 2x. Just gonna see here, this is not intersecting very well. 2x minus 2. And this is greater than, so it's going to be a dotted line. Maybe I'll go between the points. That made a much better looking line. Okay, and then y is greater than or equal to negative 5x minus 1. Okay, so I'm going to go down by 5. I'm going to go over to the 1 and over 1 and up by 5. 1, 2, 3, 4, 5. And this is a solid line, so we're going to just connect it like that. All right. Y is greater than or equal to negative 5x minus 1. So I know I need to be above that solid line, so it's going to be over here on this side. So all of this stuff is out. Okay, y is less than the one with the negative slope, so I'm below that one, so I'm kind of restricted to this area now. And y is greater than the other dotted line, so it's going to be this triangular region here, which maybe I'll shade in pink. All right. Now, Jamie works at a pharmacy for $15 an hour. She also babysits on the weekend for $10 an hour. Jamie needs to earn at least $120 a week, but can't work more than 18 hours a week, I guess, to make sure she keeps up with her studies or whatever. And so we are going to write a system of inequalities that would show how many hours she could work at each job while meeting the goals. Okay, I'm just going to let x be, hold on, let me make a decision on that real quick. Yes, I'm going to let x represent hours spent babysitting. And I'm going to let y be the number of hours worked at the pharmacy. Okay, and then the system is going to be, all right, the amount of money needs to be at least 120. So the total amount of money needs to be greater than or equal to 120. And the way that she's earning money is 15 times the number of hours spent at the pharmacy. So it'd be 15y added to $10 for each hour spent babysitting. Okay, so 10x plus 15y needs to be at least 120, greater than or equal to. And then the other one is can't work more than 18 hours each week. Okay, well that means that x plus y needs to be less than or equal to 18. Okay. So if I go and kind of find my x and y intercepts, I'm going to need an x and y intercept of 18 on this one. And I'm going to just real quickly count these off. So I've got 3, 6, 9, 12, 15, 18, 20. I think this is a 20 by 20 grid. And so I would count that again. But if it's got to be less than or equal to 18, then well, I guess that would give me half. Outer reaches. Yeah, this will be fine. Okay, so 2, 4. I just don't want to count wrong. Okay, there we go. That's 18. And then I know because this is a 20 by, actually, it looks like a square, but I guess can't be sure. 2, 4, 6, 8. 10, 12, 14, 16, 18. Yeah, it was a 20 by 20 grid. Okay, I know that y equals 18 minus x, or x plus y equals 18, ends up kind of getting this line that starts at y equals 18 and goes down to x equals 18. And that looks pretty good. All right, we're going to sketch the solution region. Okay, so x plus y is less than or equal to 18. This is where y is less than or equal to 18 minus x. So I know I'm going to be down here in this area. Okay, and I'm not interested really in negative amounts of hours worked. That doesn't make any sense. So I'm going to also graph 10x plus 15y equals 120. Okay, 10x equals 120. Well, that's going to have an x-intercept of 12, because 10 times 12 is 120. 16, 14, 12. Okay, and then the y-intercept will be 15y equals 120. If I take 120 and I divided it by 10, that would be 12. We need to divide by even more. It feels like 8. Yeah, it's because 15 times 4 is 60, so 15 times 8 is 120. So I'm here and there. I'm going to connect these dots. And you know, I didn't mention this at the beginning of the problem, but I think I'll mention it now. Of all of the problems on this review, I obviously the substitution, elimination, 2x2s, 3x3s, they're very important. You need to practice those. But as far as like something that's maybe a little bit different from what you've seen on the homeworks that is going to be on the test, it's this. Okay, and I'm going to ask a couple of extension questions beyond part C that I think are going to be helpful for that as well. So if you're still watching 15 minutes in, thanks. And this will help when you go to do the free response section of your test. Okay, graph the system of inequalities. Well, it's where the solution region is going to be, okay, where I'm below this line and above that line. So this is kind of the region of different combinations that Janine is going to be able to work while getting at least $120 a week and not working more than 18 hours. So I guess not, neglecting her studies. Okay, so identify and interpret two possible solutions. I'll do a couple, or maybe more than two is what I'm saying. We could go 0-18. We could work 18 hours at the pharmacy and no hours of babysitting. We could work 18 and 0, where we worked 18 hours babysitting and nothing at the pharmacy. Okay, and we could work some that are in between. We could work, if we were needing to work the least amount of hours possible, we could work 8 hours on Y at the pharmacy and no hours at the babysitting job and still earn exactly $120. Okay, I think that, these places are going to be where we can earn the most money, but it's not always going to be the same amount of money along this line. Okay, so that's something I'm going to ask here in a second. Another possible solution would be, let's say that's 8 and that's 8. We could work 8 hours at each job, right? And then we'd still be under 18. We could work, say, 7 hours of babysitting and 11 hours of pharmacy. That's a lot of different solutions that I've interpreted, but they were all in that pink region or on the boundary because it was a solid line. Okay, that was me identifying and interpreting potential solutions. Okay, now I'm going to bring in a couple of extra questions. Okay, part D. Janine's strapped for cash. She needs money, quick. Okay, how much, what combination of hours should she work if she wants to earn the maximum amount of money? Okay, how is she going to do that? Well, what we're going to do is we're going to say, okay, probably since, we've got all of these options, the thing about these maximum minimum scenarios is they always occur at corner points of our region, of our solution region. And so, but you can kind of just think your way through this. If she wants to earn as much money as possible, y'all know deep in here, you want to earn the most money, you got to put in the work. You got to put in the time. She's going to have to work all 18 hours, right? She's going to have to work the absolute maximum amount while still not neglecting her studies. So she's going to have to work somewhere along this 18 hours thing. And also, we want to work the one that pays more, right? Pharmacy work pays more. Pharmacy work pays $15. Babysitting only pays $10. So she really just needs to really press at that pharmacy as much as possible. And so that's going to be 18 hours at the pharmacy, none at the babysitting. And so 18 hours pharmacy, 0 hours babysitting. And if they asked you how much money could she potentially get while staying within the constraints, well, then she would say 18 hours times $15 an hour. Well, that's kind of like multiplying by 1.5. I believe that, that's going to be $270. Okay, so she can get $270 by just working at the pharmacy all week and working 18 hours there. And then part E, okay, if she already knows, say maybe 2 or 3 weeks from now, the pharmacy's given her schedule, and she knows that she's going to need to work exactly 11 hours. No, hold on. Let me think. I'm going to go look at something else and get just the right question. So if the pharmacy needs her for just, let's say, 5 hours at the pharmacy. Okay, then the question would be, what's the minimum amount of time she could spend babysitting to still earn her $120? Okay. Okay, how much babysitting? I'm just squeezing it in there. Okay, so what we're doing here really is we're just saying, okay, when we dictate 5 hours at the pharmacy, that's y equals 5. So I go over here to 5, and now I'm only along this green line that this is the end of the road for this green pin, I think, yeah. Okay, I have to stay along there. And so what's the minimum number of hours I can work at babysitting while still earning my $120? Well, this whole region, this kind of quadrangle here, this is all of the combinations that are at least $120 and no more than 18 hours. So I think it's going to be this one. Okay, it's going to represent the x-coordinate of this intersection. But I want to be certain, so I'm going to plug in y equals 5 into this equation. And this line was, I've got it over here, 10x plus 15y equals 120. So I'm going to say 10x plus 15y equals 120. That's what I'm trying to solve with y equals 5 there. So 10x plus 15, 30, 45, 60, 75 is equal to 120. I'm going to subtract 75 from both sides. Okay, 75 and 25 would be 100, so that's going to be 45. I'm going to divide over here, and so I would need to spend at least 4.5 hours babysitting in order to get at least my $120 if I'm Janine. Okay? And so that's all I've got to say about that particular example. And hopefully in a few days you will understand why I did those 2 extra problems. I was not trying to just waste your time. All right, now we're going to go over here and talk about beads. Okay, a bag containing red beads costs $2 per bag. Okay, blue bead bags cost $3. I need more bags of blue than of red, and I need a minimum of 4 red bags. Okay. Okay. So X is going to be bags of red beads. And then Y will be bags of blue. Okay. We need the number of blue beads to be more than the number of red beads. Okay. So blue greater than red, Y greater than X. I need a minimum of 4 red bags. Okay. So X greater than or equal to 4. Minimum means we could have 4. That would be fine. And I can spend at most $60 on beads where, 2 times the number of reds plus 3 times the number of Ys needs to be less than or equal to 60. All right, so I know that means that the y-intercept of this line is going to be 3y equals 60, y equals 20. This is a 20 by 20 grid. I know that's up at the top. All right. X is going to need to equal 30. So all of a sudden, I'm going to need to use a scale of 2 to 1, right? And even that is going to be, I just need to go up to 15 on X. Because it's X equals 30, I'm going to use a scale of 2. 20, 19, 18, 17, 16, 15. That's going to be 30. This is now 40, so I don't actually need that much. Okay, that's going to be my 20. All right, so 2x plus 3y less than or equal to 60. I'm just going to, I'll warn you, this is not going to be my best sketch, because we've made a lot of graphs so far here. This will be enough. And we're going to, all right, y is greater than x. Well, we know what y equals x looks like. It's just this line that goes up like this with slope 1. So I'm just trying to get it so that it runs into the grid nicely. And then we're going to make ourselves a dotted line. And I hope for the best. Decent. And that would be y equals x. Y is greater than x is going to be up above this line. We're still below the solid line. And x needs to be greater than or equal to 4. We've got a scale of 2 going here, so that's going to be 4. X equals 4 is this whole line. So this is going to be my solution region over here. Okay. So one possible solution is 6, 8, 10, 12. 12 and 12. You could get 12 bags of each right here. If I graphed it right. Okay, which that does actually kind of make sense. I could also get 4 bags of red and I don't know, how many is this? 8 bags of blue, right? Okay, I could get these numbers of bags if I wanted. These are the 2 solution points. I could also go with this number, and that would be kind of a medium number, and it would still fit the constraints. Fine, that's all I was going to say there. Okay, now, we've got a lot of systems here. So I think what I'm going to do is, and you know, I don't want this video to be like 3 hours long. So I think I'm going to do half of them this time. And then I might come back in a separate video and do the other half of the 3x3 systems. But for now, I'm just going to be working the evens. For the odds, I will give you the answer just like real quickly. Okay. So you can check your work if you're looking. And then I guess I'll have to loop back around with a separate video. But I know that these can take a long time, so I don't want this video to be ridiculously long. So I'm going to start with the evens, and then maybe I'll loop back around to the odds. Or maybe in a separate video. But if it is a separate video, it will just be linked at the end of this video. Okay, so I'm going to use this negative x as my tool to clear out the rest of the x's with elimination. Although, actually, no, I'm going to use the y's, because I've seen the 3 and the 6 and the 9. And, yeah, well, that's the same as 1 and 2 and 3, so it doesn't actually matter. I'm going to eliminate x, just like I had intended to in the first place. So I'm going to copy down the first equation. And then I will multiply the second equation by 2. Oh, man. That's tough, but it's all right. I'm going to add them together. And then I'm going to get 0 x's, 0 y's, 6 z's equaling negative 120. Add 54 back. 66. Okay, I can see that. So it would be negative 66. And I'm getting z equals negative 11. Okay. Then I'm going to take, oh man, but I can kind of see, I think it's going to work. I'm going to eliminate on these as well. But is this just going to tell me z equals negative 11 again? Okay, yeah, I'm not sure, but I was kind of angsting over how much paper I had left. But I've got plenty of sheets of paper. I shouldn't be worried about that. And, all right, get a new sheet. Go over here. I'm going to triple the second equation. Tripled. Okay, so negative 180. And then copy in the third one. All right, so if I have negative 180 and I add back 80, that would be negative 100. And I add another one, that's negative 99. And I get 9z equals negative 99, that means z equals negative 11. Again, okay, great, good that I know that, but that didn't help all that much. So what I'm going to have to do is now I'm going to have to, I guess, substitute on z equals negative 11, and then I'm going to see that I've got the same equation 3 times, I think, is what's going to happen. Okay, this is not, I hadn't had one happen like this before. Multiply by 20, multiply by 9, multiply by 9. Oh, this one's going to be no solution. This one's tricky. Okay, I'm glad I did this one. So we're going to go back into our original equations. 2x minus 6y minus 4z is going to be plus 44, which is going to be 54. Okay, that tells me that 2x minus 6y equals 10. And yes, I'm going to actually divide this whole equation by 2. Just to illustrate what I'm talking about here, I'm going to divide this whole equation by 2. X minus 3y equals 5. Okay, it might not be entirely clear to you why I would do that at this point, but I think it will be here in a second. Okay, then in the second equation, I've got negative x plus 3y plus 5z is minus 55. Yes, plus 5 times negative 11. That's equal to negative 60. Okay, so I'm going to add 5 to both sides, and I'm going to get negative x plus 3y equals also 5. Nope, negative 5. Okay, so these are the same equation. But then I'm going to go in and I'm going to do this to the third equation. 3x minus 9y minus 6z is going to be plus 66. That needs to equal 81. Okay, and so then when I, collect this all together, I'll get 3x minus 9y equals, okay, when I subtract, I'll get 15. And then I'll divide everything by 3, and I'll get x minus 3y equals 5. And so if I multiply this one by negative 1, I just keep getting x minus 3y equals 5, and that's how I know I'm going to get infinitely many solutions. So I took a few seconds to check my answer using technology, and I didn't make any errors, so I'm going to say, yeah, this is infinitely many solutions. Okay. It's just that all of the solutions happen to have that same z-coordinate of z equals negative 11. And if you're interested in what that looks like geometrically, well, then you should sign up for my linear algebra class sometime in the future, and I'll tell you all about that. All right, so yeah, that was number 10. I'm going to move on to number 12 because I'm just doing the evens right now. Okay. For the odds, I don't know, scroll forward to the end of the video, or actually, yeah, no, I'm going to just flash up the answer to number 11 real quick. No, that was a lie. I can see where this one's headed, so I'm going to just work this one. Okay, x plus y plus z equals 2, and 3x plus 3y plus 3z equals 14. I'm hoping that you're kind of getting to the point where you see that, and you're like, oh, there's something going on there. I want to just do elimination with that, and it'll be really quick. And the 2 and the 14 aren't separated by a factor of 3 the way the constants are in the other side of the equation. So it looks like bad news. 3x 3y, 3z equals 6 when I go and multiply the second equation by 2. Maybe I'll multiply the third equation by negative 1. Add these together, I get 0 equals negative 14. 0 equals negative 8. That's not true. This is no solution. Okay, so I wanted to make sure I got at least one that was infinitely many solutions and one that was no solution on here for 3 by 3, right? I wanted to make sure that happened. But now I'm going to go back to working just the evens, right? I just saw that one was going to happen, so I figured it would be worth doing. All right, now I'm eliminating on z for sure. Okay, I'm going to do, and in my class, I very seldom, if ever, subtract one equation from another, but all of these having that positive z, it makes me want to subtract an equation from another. And I've had students in my class ask me if that's okay. And of course it's okay, yes, because really what you're doing when you subtract an equation from another equation is you're adding a negative copy of one equation to another. And we know that we can add any constant multiple of an equation to any other equation while still being, still preserving the solutions of the system. So I'm going to do equation 2 minus equation 1, because although I can subtract equations from another, I would prefer for us to do the larger number minus the smaller number. So 3x minus x, that's 2x. 3y minus y, that's 2y. Z minus z is nothing, and negative 18 minus negative 2, that's negative 16. Okay? And then, well, it doesn't matter. One of them is going to be negative and one is going to be positive when I subtract these two from each other. So maybe I'll do equation 2 minus equation 3. And so I'll say 3 minus 4 is negative 1x, 3y minus 2y is 1y, z minus z, no z's. And I'm subtracting top minus bottom. Okay, negative 18 minus negative 20, that's 2. Okay. Now I've got myself down to a 2 by 2 system. I'm halfway there. I'm going to take, if I call this equation 4 and equation 5, I'm going to double equation 5 while leaving equation 4 the same. Okay, so this is equation 4, 2 of equation 5. We're going to add those together. No x's, 4y's equals negative 12. So y needs to equal negative 3. Now I'm going to go back to one of the equations in my 2 by 2 system. It's very important. I go back to the 2 by 2 to get x. I will get z last because I eliminated on z, and I will go back to one of the original equations printed in ink on my paper. Okay, but for now I've got y. I'm trying to find x. Maybe I'll do negative x plus y equals 2. In order to get rid of this negative 3 over here, I'm going to have to add 3 to both sides. Okay, so negative x equals 2 plus 3, which is going to be 5. That's telling me that x needs to equal negative 5. And I think I need to zoom out a little bit, yeah. All right, now from here I'm going to go back to x plus y plus z equals negative 2. So x plus y plus z equals negative 2. So I've got negative 8 plus z equals negative 2, and I feel like that means that z needs to equal 6. So my solution is going to be x equals negative 5, y equals negative 3, and z equals 6. And I'm going to need a scratch piece. But no, I'm not needing a scratch piece of paper for 13 because I'm just going to give you the answer. All right, number 13 comes back with a unique solution. It's x equals 4, y equals negative 2, z equals 3. If you want to see the full solutions to this, then you might, scroll towards the end of the video, or, check out the other video if I've recorded that. Okay, but this one's just going to be, I would recommend elimination on z again because the negative 2z and the 6z is over here. But that's what you'll get. Let's keep moving. Let's get number 14. I think that I'm going to need more room to work this. And if you need more room to work this, what should you do? Should you try to cram all of your work into a small area, or should you use a separate sheet of paper? Okay. The wise Algebra 2 student uses a separate sheet of paper. And so let me model that behavior for you by getting a scratch sheet of paper out and just laying that in right here. Yeah, this will be good. So I'm going to use the negative x as my tool to eliminate these other two x's. So my plan is to eliminate x. Okay, I'm going over here. I'm going to say equation 1 plus 2 of equation 2. Kind of lay it out that way. So equation 1 is 2x, 5y, 4z equaling 1. 2 of equation 2 is negative 2x plus 2y minus 2z equals 34. Add all these together, I get no x's, 7 y's, 2 z's, and that's 35. Okay, that's something. I'll work with that. Then I'm going to need to have 2 of equation 2 and add that to equation 3. Luckily, I already did 2 of equation 2, and I can just copy from over here, negative 2x plus 2y minus 2z equals 34. And I feel like, yeah, that's not in a place where you can see it. Okay, and then equation 3 is 2x plus 8y plus 4z equals 10. Yeah, I've just copied directly. And now I'm going to add down 0, 10y plus 2z equals 44. Okay, now that I've got these two equations, okay, I've got 2z and 2z here. This is good news. I'm going to make this one negative so that I can subtract 10y minus 7y and still be in the realm of positive numbers. So I'm going to label this one equation 4 and this one equation 5. So I'm going to have equation 5 and the negative of equation 4. Okay, so I've got 3y here, no z's, equals 9. So y is going to need to equal 3. Then I'm going to go back to my 2 by 2 system right here and get the value of z. Okay, I'll do 10y plus 2z equals 44. 10y is going to be 30 plus 2z equals 44. So I subtract 30 from both sides. And I get 2z equals 14, and z is going to equal 7. Okay. Now I can go back to the original system that was written in ink on the paper, and I can find the value of x. And I'm finding the value of x because that's the variable that I eliminated at the beginning. If I'd used substitution at the beginning, that would be the last variable I would find as well. Okay, so 2x, I'm going to just use the first one. 2x, yep, still on screen, 2x plus 5y, well, that's plus 15, plus 4z, that's plus 28. That's going to need to add together to all equal 1. Okay, and 28 and 10 is 38, and then add 5, that's going to be. Okay, I'm going to subtract 43 from both sides. Now I'd get negative 42, and then x is going to equal negative 21. So negative 21, y is 3, and z is 7 for number 14. All right, for number 15, I'm just going to give you the answer now. All right, it's 21, 10, and negative 28. Okay, and again, if you're interested in the solution, I might do these at the back end of the video or in a separate video. Okay. Number 16. Movie theater advertises that a family of 2 adults, 1 student, and 1 child between 3 and 8 can attend a movie for $15. All right, so, okay, Gaussian elimination. Well, I'll tell you, that's a word that we have not really talked about in this class. It's Carl Friedrich Gauss, who's a big-time mathematician from the 1800s who, you know, single-handedly advanced mathematics, they say like 250, 300 years on his own. He was the one that kind of applied the matrix stuff to what we're doing here. And if you don't know anything about matrices, no big deal. Because what I'm telling you is that Gaussian elimination, that's what we do. Regular elimination is Gaussian elimination. We just carry around our variables with us, and we don't put them in a matrix. It's exactly the same. Okay, so x is going to be the number of adult tickets. Y is going to be the number of student tickets. And z is going to be the number of child tickets between the ages of 3 and 8. Okay, an adult ticket costs as much, so x equals the combined cost of a student ticket and a child ticket. So that's y plus z. Okay, so I can already tell this is going to be set up for substitution, right? If I get x equals y plus z, I'm going to want to substitute on x. I purchase 1 adult ticket, 4 student tickets, and 2 child tickets for 23. Oh, yeah, I know it says use elimination. We're not going to do that. Okay, this thing is clearly set up for substitution, so we're going to use the one that it's clearly set up for, right? There's no sense in doing that. We're going to, what's the other advertisement? Okay, family of 2 adults. I didn't see that. I thought that was just, I don't know why they were saying that. Plus 1 student and 1 child between the ages of 3 and 8, which, you know, I error-free up to this point. Well, except for the fact that I botched up the first problem the first time I tried to record this video. But one student and one child under the age of 8, that's going to be $15. Okay, yeah, we're going to substitute here. Okay, when it's set up so clearly for substitution, trying to force your way into elimination or something is really just a good way to make an error. And I don't want you to do that. I want you to get the right solution more than I want you to be, fluent in all the types of solving. Okay. We're going to substitute on x here and there. So I'm going to have y plus z plus 4y plus 2z equals 23, which I could simplify to 5y and 3z equaling 23. And then I can take this one, and I'll say 2 times x, 2 times y plus z. That's going to be 2y and 2z. Right? Because if an costs a student and a child ticket combined, 2 adult tickets is going to be like 2 of each, right? And then plus 1y and 1z, that's going to be $15. Okay, so when I combine these all, that's 3y plus 3z equals 15. Now I'm going to subtract this equation from that equation, which is something I don't do that often, but when it's just looks really nice for it, 5y minus 3y, we can do that. That's 2y. That's going to be 0. 23 minus 15 is going to be 12. So y, a student ticket, is $6. Okay. What we're going to need is we're going to need to go back to one of our equations that just has 2 variables in it. Maybe 3y plus 3z equals 15. How is that possible? Hold on. I've made some kind of mistake here. Okay, luckily I caught the error pretty quickly. It was just an arithmetic error. 23 minus 15 is not 12. That would be 25 minus 13. That's going to be 8, so y is 4. Okay, that was not as bad as I was fearing. And then, yeah, because it was like all of a sudden the child, or the young child ticket was going to have to be a negative amount of money. That wasn't going to make sense, right? So 3y is 12 plus 3z equals 15. I'm going to subtract 3z equals 15 minus 12 is 3. Z equals 1. Okay, so child ticket's $1. Student ticket's $4. That must mean the adult ticket is $5. So I've got x equaling $5, y equaling $4, and z equaling $1. You can check your solution against our original equations, but yeah, that's going to work out. 5 and 16 is 21, and 2 is 23. 10 and 4 and 1, yeah, that's 15. Okay, cool. I'm satisfied. All right, and we've got just 2 more situational problems. And, all right. All right, now this last one that's talking about an augmented matrix, we didn't do that this year. Use a calculator to solve. We definitely didn't do that this year. Don't get any ideas in your head about solving with a calculator. We are going to do that in this class. We're just going to do it in the second semester once we're really focusing on how we can use technology to advance our study of algebra. Okay. So on this one, I'm going to run the solution real quick and make sure that it's going to come back integers. If it is, then I'm going to do it by hand. But for now, let's do this one because I can tell this one's going to be fine. Okay, a taster pack of fruit costs $22.50 for 1.5 pounds each of peaches, which I'm going to call X, blueberries Y, blackberries Z. All right, so 1.5 x plus 1.5 y plus 1.5 z is equal to 22.5. Okay, I can tell you probably the first thing I'm going to do once I go to start working on this system is I'm going to multiply this whole equation by 2 because I don't want to deal with 0.5s at all. Okay, $39 is 3 pounds of peaches and blackberries and 1.5 pounds of blueberries. And that costs $39. Who knows, maybe I'm just going to subtract some equations from each other. A family pack is $51. 3 pounds of blueberries, that's 3y, and blackberries and 4 pounds of peaches. All right. Okay, yeah, we're not going to use our calculator because that's not something we've been doing in this unit. Okay, we're going to use elimination on this one. I'm thinking, let's eliminate on z by multiplying the top equation by -2 and the second equation by -1, and then just, kind of using equation 3 as my tool. It doesn't really matter. You can do whatever you want. But I would recommend using elimination on this one. Unless 22.5 is divisible by 1.5, which I think it is. I'm tempted to use the calculator. But I'm not. I'm not going to, right? Too disciplined. I'm not going to do it. Okay, so I'm going to take basically, equation 3 minus equation 2. And yeah, that's still visible. 4 minus 3 is 1x. 3 minus 1.5, 3y minus 1.5y is 1.5y. That's going to be, no z's, is 51 minus 39 is 12. Then I'm going to take equation 3 and subtract 2 of equation 1. Yeah. 4 minus 3, okay, so yeah, 4x minus 3x is 1x. 3y minus 3y is 0y. 3z minus 3z is also 0z. 51 minus 45 is going to be 6. Okay, good for us. Lucky for us, really, right? Because now I'm just going to substitute over here and say 6 plus 1.5y equals 12. Okay, I'm going to subtract 6 from both sides, and I'll get 1.5y equals 6. And, okay, if you could think about what's a number I multiply by 1.5 to get 6, and if you know that's 4, good for you. If you don't see that, I think one thing I could safely expect is that you know that 1.5 is the same as 3 divided by 2, and then you could multiply both sides by 2 and then divide both sides by 3 to see that y is going to equal 4. Really however you want it, right? And then z is going to be something I'll have to find from one of my original equations. I'll just say I'll use this one. It's got all nice whole numbers. 4x is 24. 3y is 12. 3z is what I'm hoping to find. That's going to add together to be 51. So I've got 36 and 3z equals 51. Okay, I'll subtract here, and that's going to be 3z equals 15, and divide by 3, and z is going to be 5. Okay, so the peaches are costing $6 a pound, the blueberries are costing $4 a pound, and the blackberries are costing $5 a pound. All right, number 18, the last one. Okay, rather than just showing you what the answer is, I think what I'm going to do is I'm going to set up the system. I'm going to solve it off to the side while the video recording is paused, and then if it's a good solution, then we'll do it all together. How about that? All right, so sells 3 items for the regular price on Monday. The total of the regular prices of the 3 items is $48. So I guess this must be A plus B plus C equals 48. Yes, item A is half price, B is regular price, item C is a third the regular price. This happens $31. Okay. On Wednesday, the store sells item A for half price, plus B at a quarter of the normal price, and item C for the regular price. And then the cost of all 3 items on Wednesday was $28. Okay, so we're going to find the regular price of each item. Okay, yeah, and so, that's... Really, this is our augmented matrix, is the secret I'm going to spoil for you, is that we've got it right there. It's just got some letters in it and some equal signs. But I'm going to, I don't know if you just heard me pull out a calculator, but I'm going to check the solution real quick. Yes, technology was not needed for this one at all. Yeah, this one's going to work out really nicely. I'm just going to give myself more room to work here. All right, so what I'm going to do is I'm going to get these out of the fraction world and into the whole number world, and then life will be good. Okay, I think I'm going to maybe try to just eliminate, no. I should try to get rid of all the fractions and then figure out how I'm going to eliminate. So I've got, in fact, I might scoot it down just a little bit so that I can just kind of, okay, I don't need to do anything to this equation. Everything is already whole numbers. This, I've got a half and a third, so I need to multiply everything by 6 to get rid of all of the fractions. So 6 divided by 2 is going to be 3a, 6b, and 2c, right? So I've got to multiply everything by 6. 6 times 31, that's kind of a stretch for me, but I can do it because 6 times 3 is 18, so it's 180, and 6 more is 186. Okay, and then this one I'm going to need to multiply everything by 4. Right? Yeah, to get rid of that. So I'm going to have 2a plus b 4c equaling, okay, you got to multiply 28 by 4. And again, that's a bit of a stretch, but I see 25 times 4 is 100, and 3 more times 4 is 112. All right, now I've got a 3 by 3 system that looks like a little friendlier on me. Right? It's not going to be, I'm not going to have to deal with fractions, okay? I'm going to have to deal with big numbers, but me personally, I would rather deal with big numbers than deal with fractions, okay? So we're over here, and I'm going to say, all right, how am I going to proceed? I could really do any of these. I think to avoid having to multiply equation 2 by anything, I'm going to eliminate on... Okay, yeah, multiplying equation 3 by 6 is a little much. So I think what I'm going to do is I'm going to eliminate on A. Yeah, and so I'm going to do -3 of, this is going to be equation 1. This is going to be equation 2, and this will be equation 3. Yeah, all visible. So I'm going to do -3 of equation 1. (48 times 3 is 120. And 24 more is going to be 144. Except that's going to need to be negative because it was -3 times everything. Then 3a plus 6b plus 2c equals 186. Okay, yes, these numbers aren't going to be so bad. That'll be 3b minus c equals, okay, 186 minus 144 is going to be 42. Yes, okay, that seems reasonable. Okay, that, and then I did, that was -3 equation 1's plus equation 2. Okay. Then over here, to get rid of this a, I'm going to do -2 of equation 1 plus equation 3. And a plus, nope, I need that to be -2a minus 2b minus 2c equals -96, because I've got to multiply everything by -2. And then equation 3, I'm just going to copy plus b plus 4c equals 112. Okay, now I'm adding together no a's, -1 b's plus 2 c's. That's going to equal, let's see what we got here. 96 and 4 is 100, so that's 16. All right, now that I've got it down to a 2 by 2, maybe I'll cover that up real quick, and I will combine these. I'm going to try to eliminate c, right? Because I'd rather, well, maybe I should maybe I should eliminate b. Right, to keep myself from having to multiply this by too much. It doesn't really matter. You're going to do the same arithmetics no matter what. So, yeah, I might copy 3b minus c equals 42, and then triple this one. Okay, so, yeah, okay. Hold on. No, we're good. So -3b plus 6c equals 16 times 3 is 48. And I'm going to get, when I add this all together, I get a total of 5 c's equaling 90. Okay, so that tells me that c is going to need to equal 18. Okay, if I divide 90 by 5, I will get 18. Because dividing by 5 is in some ways like multiplying by 2, except then you have to cut off a decimal place. But now I've got c equals 18. I'm going to go back over here to get b. 3b minus c equals 42. Why not? 3b minus c equals 42. I'm going to add that over here, and I get 42 and 18 is 60. So b is 20. And then lastly, I'll get from one of my original equations, right? I'm going to need a plus b plus c equals 48. That's what I need to be working with. So c is 18, b is 20. A plus b plus c equals 48. That's telling me that's 38, and a needs to be 10. Okay, that's going to be the prices of all 3 items. And that was workable by hand, I think. Let me just check in and make sure. Okay. Yeah, okay. Yeah, 10, 20, 18. Yeah, that's what I got. All right. That's all the problems, but I think I might go back in now. Yeah, I've got enough time. I'm going to go back in now and work those other 3x3s. The rest of the problems did not take as long as I expected them to take. It's going to be numbers 13 and 15, which I did already show you just the answer for, but if you saw just the answer, how am I going to get the full solution? That's what I'm about to help with. All right. Let's see, this one's already written on, but I got plenty of scratch paper. All right, on this one, I'm thinking we're going to eliminate on z. Okay, that's my plan, is I'm going to eliminate z using that negative 2z. So I'm going to take equation 1 and add 3 of equation 3 to it. Okay, so let me see, it's the edge of my shot. Equation 1, and then 3 of equation 3. So that's 2x plus 4y plus 6z equals 18. I'm just copying that. And then I'm tripling this one. 9x, 3y, negative 6z equals 12. I can add those all together. And I'll get 11x, 7y, no z's equaling 30. Okay. Then I'm going to take equation 2 and eliminate z. So I'll take equation 2 and I'll add 3 of equation 3. I'll just get that down a little bit. And equation 2, I'll just copy that directly. Okay. 3 of equation 3 is 9x, 3y, negative 6z equaling 12. Is that the same as I got before? Yes, good. That's a good sign. Okay, add this all together, and I'll get 13x, 8y, equals, that's not good, but, you know, probably good that we run into like a worst case scenario on the review, just in case that happens on the test. I'll tell you, I'm pretty sure that's not going to happen, where we're going to have to multiply one equation by, say, 11 and another by 13. Realistically, 7 and 8 is what I'm going to do, but that's kind of a lot. Okay, let me make sure I didn't, you know, make any critical errors. Nope, I can't see it if I did. 12 and 18 is 30, 12 and 24 is 36. Okay, we're good. Can't do anything else. So what I'm going to do is I'm going to say, all right, I'm going to need to multiply. If I'm trying to eliminate on y, I'm going to have to multiply this one by 7 and this one by negative 8. Yeah. All right, 13 times 7 is going to be 70, and 21 is 91. Okay, so 91x, multiplying everything by 7 here. plus 56y equals 210, and 42 is 252. Trying to model solving these problems without the use of a calculator, but this one's going to challenge me, I know. So and then this one I need to multiply by -8 so I can get that -56y and eliminate y. So -8 would be -88x minus 56y equals -240. Okay. Notice that if we just thought about it, we're pretty strategic about it, and just had faith, the numbers are going to work out all right. Okay, this is going to be just 3x equaling 12. So that's x equals 4, which, right, we were expecting. All right, now I'm going to go back over here to one of my original easier number equations. I like 11x plus 7y equals 30. So I've got 11 times 4 is 44 plus 7y equals 30. Okay, yep, that's all right. I'm going to subtract, I'm going to have to go down here, subtract 44 from both sides, and I'd get 7 equals -14, and y equals -2. Okay, that's good. And then I'm going to use the top equation at the top of your screen, 2x positive 4y plus 6z equals 18. Oh yeah, 6z equals 18, z equals 3. Okay, so 4, -2, 3, that is what we were expecting to get. That's good. Okay, so this one, it would have been really easy to give up right here, where I saw that I was having really bad numbers. Like, you know what, this is a review. I'm on the 3rd or 4th page of it, and is he really going to check all the pages? Who knows? It would be really easy to not take this problem all the way through, but if you did, good for you. That's what I'm saying. Hard work will pay off. We do believe that. All right, so the last one I'm going to be doing for you here today is going to be number 15. And I've got 3x, 5y, and 4z combining to equal 1. -x plus y minus z equals 17, 2x, 8y, 4z equals 10. All right, I feel like we could go any number of ways. I might... If I knew 17 times 4, 68? I guess I'd never done 17 times 4 before. I'm sure I have, but yeah, I'll do that. And so that I can eliminate on z. So I'm going to take equation 1. Yeah. Just copy it directly. Multiply equation 2 by 4. So -4x, positive 4y, -4z equals 68. Add these all together. And we're going to add, and we'll have -x plus 9y equals 69. And then if I want to eliminate z out of equation 3, I'm going to take, maybe equation 3, and I'll just copy that. Plus 8y plus 4z equals 10. Is that visible to you? Yes, just barely. And 4 of equation 2. It's going to be -4x plus 4y minus 4z equals 68. Add all this stuff together. I'm getting -2x plus 12y, no z's though, equals 78. Okay, so maybe I would multiply this one by 2 and this one by -1. I'll just multiply this one by -2. So I've got 2x minus 18y. Okay, if I doubled 70, I'd have 140. So if I double 69, I must have 138. But I'm multiplying by -2, so that'll be -138. And then I will add this -2x plus 12y equaling 78. And, okay, I see what's going to happen here. This is going to become 60. negative 60, right, because the 138 is bigger than the 78. And I'll end up with negative 6y, telling me that y needs to equal 10. Then I can go back to one of my 2x2 equations. I'd probably take one that I hadn't already manipulated. Maybe I'll take this one that just has negative x. Negative x plus 9y equals 69. So if I take 69 and I subtract 90, I think that's going to be negative 21. Because if it was 70, it would be 20, yeah. Okay, so negative x equals negative 21. So x equals positive 21. And then we'll go all the way back to the easiest looking middle one up here. So negative x plus y minus z equals 17. That's negative 11 minus z equals 17. So I need to add 11. So negative z equals 28. So I think z is negative 28. And let's just check our solution. 21, 10, negative 28. Yep, that's what we've got. All right. That was a good amount of systems of equations. If you, oh, I just threw away my pen. I need to throw away my sheets. If you need more practice on substitution elimination on 3x3s, I've got more of those. I haven't recorded the solutions yet, but I am resolved to, sometime before the test. And I will link those extra practices if you're feeling like you need them in the description of the video. Otherwise, thanks for watching. Really hope this helped.